Hello, my dear students. Last class, I explained about the different types of spillways. Let us continue with that, the different types of spillways. The next one is conduit or tunnel spillway. A tunnel spillway is the one in which a closed channel is used to convey the discharge around or near a dam. The control structure for this spillway may be in the form of an overflow crest, vertical or inclined orifice entrance, and side channel crest. The tunnel is designed to flow partly full, and it is not allowed to flow full because a siphonic action may develop due to negative pressure being developed in the tunnel, where a closed channel is used to convey the discharge around a dam through the adjoining hillsides. The spillway is often called a tunnel or conduit spillway. The closed channel may take the form of a vertical or inclined shaft, a horizontal tunnel through earth or rock, or a conduit constructed in open cut and backfilled with earth materials. Tunnel spillways are advantageous for dam sites in narrow gorges with steep abutments or at sites where there is danger to open channels from rock slides from the hills adjoining the reservoir. You can see here this is looks like a tunnel here also, and this is high flood level. This is full reservoir level. You can see here. Okay. So shape is like tunnel. Okay. Let us go through the other type, that is drop inlet or shaft or Morning Glory Spillway. A shaft spillway is a type of spillway which consists of a vertical shaft followed by a horizontal conduit. The surplus water enters into the vertical shaft and then to the horizontal conduit and finally reaches the downstream of the channel. A shaft spillway is used at the sites where the conditions are not favorable for an overflow or acute spillway. If the inlet leg is provided in shape of a funnel, it is called Morning Glory Spillway. It has maximum discharge even at low heads. Water drops through a vertical shaft in the foundation material to a horizontal conduit that conveys the water past the dam. Lower end of shaft is turned at right angle and then water taken out below the dam horizontally. A shaft spillway consists of three main elements. The first one is overflow control weir, second one is vertical control, and third one is closed discharge channel. The vertical shaft of large structure is usually made of reinforced concrete and the horizontal tunnel is tunneled in rock. There are two general types of shaft spillway. The first one is standard crest type and second one is flat crest type. You can see here this is a shaft or the drop inlet or Morning Glory Spillway. Okay, see here this is the shaft spillway. Okay, you can see here. Let us discuss with the next one, that is Siphon Spillway. A siphon spillway is a type of spillway in which surplus water is disposed to downstream through an inverted U-shaped conduit. It is generally arranged inside the body or over the crest of the dam. It is commonly used in practice. This type of siphon is also called a saddle siphon spillway. It works on the principle of siphonic action. It consists of a siphon pipe whose inlet leg is kept just below the normal pool level and an air vent kept at normal pool level is connected to the crown of siphon. When the water rises the pool level, siphonic action starts automatically and the water discharges to the downstream side. When the water level falls below the pool level, air is entered through air vent and the discharging of water stops. A siphon spillway may be constructed in the body of a concrete dam when space is not available for an overflow spillway. Disadvantages of siphon spillway. The flow would result excessive vibrations in the dam body, which may cause expansion problems in the joints. There is a possibility of cavitation for negative pressures, which is affected by the head between upstream and downstream water levels. Repair and maintenance of siphon spillways are difficult. It has a limited capacity. So these are the different types of spillways. Okay, this is the example for siphon spillway. Okay. Here is an air vent, exit lip of wood, siphon duct, throat, air vent, entrance lip of wood, inlet or mouth. Next, let us discuss some special types of spillways. Apart from the commonly used spillways, a few other types of spillways are used, sometimes for a project, which are explained below. Saddle spillway. In some basins formed by a dam, there may be one or more natural depressions for providing spillway. They are sometimes preferred for locating main spillway or emergency or auxiliary spillways. A site which has a saddle is very desirable and economical if the saddle is suitable for locating the spillway. Next one is fuse plug. It may be a simple earth bank, flashboard or other device designed to fail when overtopped. Such plugs may be used where the sudden release of a considerable volume of water is both safe and not over destructive to the environment. The saddle spillway may be constructed as an earthen embankment dam with its crest at a slightly higher elevation than the high flood level of the reservoir. In the occurrence of a flood greater than the designed flood, which may cause a rise in the reservoir water, would overtop the earthen embankment dam and cause its collapse and allow the flood water to safely pass through the saddle spillway. Next one is Sluice Spillway. The use of large bottom openings as spillways is a relatively modern innovation following the greater reliance on the safety and operation of modern control gates under high pressure. A distinct advantage of this type of spillway is that provision can usually be made for its use for the passage of floods during construction. One disadvantage is that once built, its capacity is definite, whereas the forecasting of flood is still indefinite. A second disadvantage is that a single outlet may be blocked by flood debris, especially wherein flow timber does not float. So this is about the sluice spillway. Next, let us discuss about the design of Ogee or overflow spillway. The Ogee or overflow spillway I already explained. It is the most common type of spillway. It has a control weir that is Ogee or S-shaped. It is a gravity structure requiring sound foundation and is preferably located in the main river channel. Okay. It is constructed by using a portion of dam as overflow section, provided in valleys with sufficient width to accommodate the required crest length. Might be either controlled or uncontrolled. Controlled spillway, that is permanent gate, lifted automatically or operationally, or provision of temporary planks, wooden planks in small and less important spillways. Permanent crest gates increase total cost of dam, but they increase reservoir capacity. This is the figure shows the principle of derivation of crest profile. This is the origin, the crest and height HD, and this is HA, and here you can see this is the origin point, lower nape and sharp crested weir. The rate of discharge over entire length of the spillway is given by this equation. Q is equal to CLH to the power 15, or Q is equal to small q is equal to capital Q divided by L, that is equal to CH to the power 15, where C is equal to coefficient of discharge. Usually it is 2.15 to 2.2, and L is effective length of weir, that is in meter. H is measured head above crest. Q is discharge per meter length, meter cube per second per meter, and Q is discharge, that is meter cube per second. The basic shape of overflow Ogee spillway is derived from the lower envelope of the overall nape flowing over a high vertical rectangular notch with an approach velocity V0 equal to 0 and a fully aerated space beneath the nape P is equal to P0. This is the overflow spillway shape derivation. Okay, upstream water level, this is the upstream water level, and here this is H and V0 equal to 0. This is the horizontal force, and this is the A, B, C. Discharge characteristics. Similar to the crest profile, the discharge characteristics of the standard spillway can also be derived from the characteristics of the sharp crested weir. The weir equation is in the form of Q is equal to C into square root of 2G LHE to the power 3 by 2, where Q is equal to flow rate, meter cube per second, C is equal to the dimensionless coefficient of discharge, L is the crest length of perpendicular to the flow, and HE, that is the total head on the crest, including the approach velocity head. If the discharge Q is used as the design discharge in above equation, then the term HE will be the corresponding design head HT plus the velocity head HA, that is HE is equal to HT plus HA. For high Ogee spillways, the velocity head is very small and HE is nearly equal to HT. Overflow spillways are named as high overflow and low overflow depending upon to the relative upstream depth, that is P divided by HT. In high overflow spillways, this ratio is P divided by HT is greater than 1.33 and the approach velocity is generally negligible. Low spillways have appreciable approach velocity which affects both the shape of the crest and the discharge coefficients. This is a definition sketch to overflow spillway section. Approach head here. This is a pool elevation. Design head HT. This is HA. So the equations: point of tangency, y-axis. This is x-axis, crest axis. If you have if you have P divided by HT value, you can find what is CD value. Once if you have CD value, you can substitute in this equation and get what is discharge. Okay. Then this figure gives the variation of CD, the value of C when H equals the design head HD, with the relative upstream depth P divided by HT. Here, P is the height of the spillway crest with respect to the channel bed. This figure shows the coefficient of discharge for flow under gates. Overflow spillways frequently use undershot radial gates for releases over the dam. The governing equation for gated flows is given by, in this equation, Q is equal to 2 divided by 3 into square root of 2G CL into H1 to the power 3 by 2 minus H2 to the power 3 by 2, where C is a coefficient of discharge and H1 and H2 are the total heads to the bottom and top of the gate opening. The coefficient C is a function of geometry and the ratio D divided by H1, where D is the gate aperture. You can see here, this is a sharp crested weir, head on weir, Ogee Spillway at design capacity. This is HD and this is H and this is YE. And Ogee Spillway when flow exceeds design capacity. Here this is excessive turbulence, separation and cavitation, design head. Then Ogee Spillway with the ramp to provide protection from cavitation. That is, the ramp is provided here, aerated cavity here, and this is a concrete saved corbel. Triangle represents stability requirements. Ogee Spillway with corbel. Spillway crest needs a careful design to stand maximum flood. At design head, H is equal to HD. Water flowing down the spillway remains in contact with the surface and no negative pressure gets developed on spillway surface. If H is greater than HD, negative pressure gets developed, that is cavitation on spillway surface, but no such problem for H less than or equal to HD. This is about the design of Ogee Spillway. I hope all of you understood. Thank you.